Hello, everyone. So today, I'm going to talk about some basic concept about probability and also the Laplace experiment. And that's the basic type of model we will explore in this class. So after we handle that, we can move on to more advanced models and like probability measure and what's a probability triple in the next several lectures. Okay, so let's begin. This is a slide I used by Professor Alexander Gissing from spring 2022. And the first thing I want to ask about is what is actual probability? So it's a title of this course, but it has more meanings. It's a measure of likelihood or chance which an uncertain event will occur. And this definition is somehow abstract for beginners. So we'll see more examples later on. And for now, this is not compared to other field of mathematics like the geometry or even like to say algebra is have like thousands of years development. But for probability, it's originates from like maybe less than 400 years before and formalized as a distinct branch only about like maybe less than 100 year because I'm assuming that the man will formalize that after he's 20 years old. Okay. But that's probably, that's not for sure. Maybe he formalized that at 18 years. That's probable. So after this course, maybe you will have have a better understanding how likely it is over 100 years. All right. So first we'll talk about one thing: experiment. Experiment is any activity or process whose outcome is subject to uncertainty. This for example, like rolling a dice, you roll a dice, and when you are roll a dice, you don't know what the outcome is. It can be one, can be two, can be three, can be four, can be five, can be six. We're talking about like a very common like six-sided dice. So in that case, it's uncertain when you are playing. So the outcome is subject to uncertainty. Bitcoin price next year, of course, you don't know for next year what the price will go. Maybe it's zero, maybe it's 1 billion per unit. All right. And multiple weather, uncertain. Genetic variation in the population. Or we can deduce that by some method or I'm not very familiar with that, but it is also uncertain before it is coming out. So that's experiment. So usually, like when scientists talk about experiment, they're talking about an event. They don't know like they don't have already have a conclusion or result. So they do an experiment to see what the outcome is, and they go back to check whether they are like the hypothesis is correct or not. So this is experiment, and also the most important thing about like a probability is sample space. Sample space. This is like all the possible outcomes of the experiment, as it says here. It's a set of all possible outcomes of the experiment. We denote usually by the omega. By this sign, usually by omega. But if you want to denote it as a number like letter A, B, or C, that's okay. It's not fixed. So when we are throwing one die, so all the possible outcome. So 1 is possible, 2 is possible, 3 is possible, 4 is possible, 5 is possible, 6 is possible, but 7, 8 probably not possible. So the possible outcome, the set is that. And if you toss a coin twice, in here we represent the head by H and tail by T. And here we can see if you toss a coin twice, there's 4 possible outcomes: head and head, head and tail, tail and head, and head and head. So there might be some misunderstanding about like tail and head and head and tail. So here we assume that the order is matter. Order is matter, which means like the first coin is a head. The second coin is a tail. It's different from like the first coin is a tail and the second coin represents a head. All right, and also like Bitcoin price next year, all the possible outcomes, it can go infinity because we don't know how high it is. You can always find a bound higher than the price you already set. So that's go to infinity. But here it says like 0 may be the lowest. But I would like to say that maybe we can go negative values, which means like if you own like 3 Bitcoins, you must pay people like 3. That's a joke, but it's possible. So so that's so I really worry about that part. It might not be 0, but it might be like negative infinity. So that's the sample space for Bitcoin price next year. All right. And for now, we have already defined like a subset, like a sample space, and what is experiment, and now event. Consider first we will talk about outcome. Like outcome is a single possible value in the sample space set. So 2 is outcome, 3 is outcome, 4 is outcome, and events are subsets of sample space, which means like for example, we can see from here, you rolling an even number with a die. This is an event. Event means we already define it to be like that. And the only thing we are unsure is that possible, or if it's that is not possible, but it's already fixed, it's defined. So here we can say rolling an even number with a die, which means like we can set a letter to it. It's use A to represent this event. So A is equal to 4, 2, and 6. And this set, obviously, it is a subset to the omega here. And also like tossing a head at least once when tossing 2 coins. And in this sense, what's the event? The event is 2 heads and 1 head for each. So it's 3 outcomes possible. And it's also a subset of this one, the omega. Okay, and for like Bitcoin price next year, it can be okay. So let's say it's about like 50,000 to 100,000. So this is also a subset of the omega subset, and of course, it's a subset of like from negative infinity to positive infinity. All right. So this is the third definition of the event. And also like for the we usually use the outcome, use the sign like this may be I don't know how you call that. I would call it W or like fancy W. Okay, so the fancy W is outcome of an experiment. So say event A occurs if the outcome belongs to A. So outcome is a single like I'll say it's a single value in this set. So because you only throw the 1 dice once, so it must be one single. So the outcome can be 5, can be 2, can be 3, can be 1, but it's not able to be like 1 and 2 because that's impossible. You just do it once. You are not repeat this experiment. So as that we can see, if we throw the outcome is 2, and 2 is inside this event. So you can say that the event A occurs because 2 is inside A. So yeah, so this is this example here. So the die lines on 2. So event A occurs, and if you toss a coin shows tail twice, and the outcome is tail and tail, so it's double T. But double T is not inside the event B here. So we say like event B is not occur if the fancy W is equal to double T. That's what we represent here. And also like the Bitcoin price next year exceeds 300. So event C doesn't occur because okay, so it here exceeds 300, maybe it says 300,000, so the set is like that. So obviously from a real number, you can form the real number axis and see that okay, this set is not joined with this set. So here we say like event C doesn't occur. So hopefully you already understand what's experiment, what a sample space, and event and outcome. These are 4 different things, but those are like the each represent a very important concept in calculating probability. So now we move on to some like the definition probability. For now, don't try to like say, okay, this is a definition of probability. This is not definition. This is an informal definition, which means we will reformalize that later. But for now, we can already see something from those four concepts. So first, excuse me. So let omega be the sample space, and I don't know what this called also. So I call this fancy A because it looks more fancy than A. Okay, so so let omega be a sample space, a fancy A be a collection of events in omega. We define the probability measure by assigning each event A to fancy A, a number PA. A PA here means the probability of event A between 0 and 1. So probability is in a range of 0 to 1. It can never below 0 and exceed 1, but it can be equal to 0 and 1. All right. So what's this fancy A actually means? It's a collection of events. So event here is a subset. Event here we define as a subset of sample space. So when we talk about this fancy later, it will turns out that it's a power set of the omega. It's a power set of omega. But here, the collection of events, yeah, it's a power set of omega. It can never be anything when it's fully defined. So the probability of a sample space must be like calculating each event once. Like what's for example, if you're throwing a dice, if you're tossing one coin twice, and you want to ask like B is an event, or what if like tossing tails at least once? So we define it as C, and C is equal to head tail, tail head, and tail tail. So C is equal to that, and we'll calculate the probability of C and B and all other possible events from this sample space. So that's probability. And there's two views about probability in history, and they are still growing with different trends. So the frequentist is one view. So they're talking about so we already know that because for example, if you're tossing a coin for like infinitely times, maybe not infinite, but like 1 billion times, and the result of like showing heads will be like very close to like 500 million, which is 0.5 frequency. Is that it's 0.5 relative frequency. So here, we'll say the probability A, or the A means like okay. So now we say A means the coin shows heads. Is equal to like number of times A occurs in n trials. So n can be any natural number and divided by n. So we can use this view to predict what behavior of very long-term behavior, like a long-run relative frequency. So that's frequentist view about it. So if we have like do an experiment many times, repeated it in a long way, and we can use that trend to try to deduce what's the behavior when it goes to infinity. So this is a frequentist view, and also for the Bayesian view, this is totally different. It means like okay, because we are already calculating probability, like what's the probability of a ring tomorrow is 40%. So we can always use what we believed before to predict future behavior. That is not based on like we already have a repeated event, but based on like history of like history of accumulation for this event occurs, and we can assume that tomorrow it's not really likely to rain. if it's like 40%. So that's Bayesian's viewpoint about probability. All right. So in next section, we are talking about Laplace experiment. Laplace experiment. This is the introduction to the probability models, and it will be most easy because, as it said here, simple events are subsets of sample space that contain only one outcome. So in Laplace experiments, we're only consider events that are simple events. So it will reduce a lot. Imagine like if you throw a die once, so all the result will be 1, 2, 3, 4, 5, 6. So there's like 6 simple events in that experiment. But if you consider like all the events, it will be many more. And like 1, 2 can be considered 1, and 1, 2, 3. And if you have like if you try to calculate that, it will be like 2 to the power of 6, because for each element here, 1, 2, 3, 4, 5, 6, it can exist or not exist in that sample. So that's like 2 to the power of 6, which is 64 subsets. But if you only consider like simple events, that's 6, which is equal to the cardinality or set size of the omega, the sample space. So here we define the Laplace experiment. Laplace experiment is suppose we already know all outcome of an experiment with finite sample space omega. So here we already define omega, and all the outcomes are equally likely. That means that we are tossing a fair coin with half the chance for head and tail each, or the dice is fair, which means you have like 1/6 probability to get 1, 2, 3, 4, 5, 6 each. Those are called like the outcomes are equally likely, which or in another sense we say is uniformly distributed. Okay, and then for all the events, for all the events belong to that sample space, we can calculate very simply. It's a number of simple events in A divided by number of simple events in omega. All right. So, and we call like the P is a Laplace distribution over omega. So maybe like you are not familiar with distribution, but distribution is like a probabilistic distribution. Is how do you describe that? It's like if you right, if it's a continuous distribution, it has a shape like in what outcome it has more values, or in what values it has less probability. So for example, if we can say about if we plug in the values like A is okay, let me see. So yeah, so we'll discuss like what's a distribution in this example. So it has like has outcomes, so we can discuss that more easily. So so here I would say there's some properties about Laplace experiments. So first of all, the probability of event small sample space occurs 1. That is maybe it's easy to understand, but we'll see the proof later. And also for disjoint events A and B, so 2 events are disjoint, which means no elements are like overlap in A and B. Yeah, here, so it means like A intersect with B is an empty set. So in this sense, we can say A union with B, the probability of A union with B is equal to probability A plus probability of B. So that's another property. So we'll see the proof here. So why we say okay, so why we know if Laplace, if one experiment is a Laplace experiment, why the probability of the of omega, the sample space is 1. So we'll use the formula here because we define it as simple events in A divided by simple events in omega. And here, so by the definition of Laplace distribution, the P omega is equal to the number of simple events in omega divided by number of simple events in omega, which is the same. So the result is 1. So this is obvious. But for the second one, it might be hard to think about. But I really encourage people to understand the proof by first sense, so they will very easily remember why it is true. So because A and B are disjoint, so they do not share any common elements. So first thing we want to think about is simple events in A and B in A union with B is equal to the number of simple events in A plus the number of sample events in B. How to understand that? For example, there's two sets A and B, and they are disjoint, which means they are not joined together; they are separate. So when we consider like the union of A and B is just like plus them together. So this is from the sets theorem. So I will not talk about like the rigorous proof here. So therefore, the probability of A intersect with B is equal to so first of all, the denominator is the number of simple events in omega, and the numerator is the number of events A plus the number of simple events in B. So that's the numerator. And by the high school algebra, we can see that if the denominator is the same, we can separate out into this form. So it's the two term plus together. So we get, so this term also, we can see from this formula, the probability A is equal to this. So this is probability A, and this is probability B, which means these two terms are logically equivalent. So we are done the proof here. So these two properties were already proved. So in this example, I will also show what the distribution is. So suppose we toss a fair cone one time, and find the probability triple. So probability triple means it's a triple with 3 terms inside. So in the first term is the sample space. And second is the fancy A, which is the power set of all events, and also the probability set, probability distribution, which is the probability measured for each element in this power set, the fancy A. So let's describe it. So if we toss a fair cone once, so it only toss once, right? So so the possible outcome is only 2, either it's a head or a tail. So in this case, the sample space is a set of head and tail. Okay, and all possible subset. So we'll take a subset of these sets specifically. So we have empty set is a subset, H is a subset, T is a subset, also HT is a subset of that. So this gives you a much more better understanding of what a fancy A is. And since the cone is fair, we can use this use probability to describe each of these terms. So probability of PH equal to probability of T, because there is a fair cone, so each get half a chance, so it's 1 over 2. Here, like probability of empty set is 0. Why? That's obvious, because if you toss a cone, obviously you will at least get 1 outcome, so it's impossible. There's no outcome. And also, probability of H and T is 1, because whether you get an H and whether you get a T is inside this set. It's inside this is event, because the fancy is a collection of events. So it must lies in this HT event, which is the sample space. So it's equal to 1. So here we already this is the same logic for this property. Okay, so once we describe this events, I want to say like the distribution, the Laplace distribution is those terms 1/2, 1/2, 0, and 1. So it is it's very hard to think about it, but that's a distribution. When you are thinking about when you distribute things, out, when you distribute like there are four numbers, you distribute 2 into 1 people and 1 to each people. So this is the process of distribute. And here we distribute the probability for H and T to be 1/2, and we distribute the probability for empty set to be 0, and we distribute the probability for the sample space H and T set to be 1. So that's the Laplace distribution. And here we see also we notice that when we are writing this formula, we write the set of H inside the probability, which have 2, like 1 bracket here and another bracket here, which is a little bit like a little bit more difficult to write. So this is when we are like doing like a lot of calculation later, it's not very friendly to write too much things there. So we can, if we understand this is event and not outcome, we can drop the bracket down. So we just write P with the bracket, 1 bracket, and say H. We can get rid of the bracket outside H to represent the set. So this is if it doesn't cause like ambiguity to you, that's totally okay. And we also see another example. It's about a simple lottery. Okay, suppose we buy a single ticket in the lottery with 10,000 tickets and only 1 prize, which means okay, there's only 1 possible that you will win the lottery, and anything else you will lost money from that. So we think of this experiment as having 2 outcomes: success or win the prize, failure, don't win the prize. So find probability of success and failure. This is we can use here is one is about, okay, it's a Laplace experiment. Why? Because you can draw like all of the tickets with equal chance. So that's like the definition of Laplace experiment. And also, the number of outcomes in the failure set and in the success set. In the success set is 1 because there's only one outcome, and in the failure there's 9,999 because there's 10,000 minus 1 is all failure. So just as we say, we denote these failures by so each of them by 1 set, like F1, F2 to F9999. So there's also 1 success S. So what's the so we can first calculate what's the probability triple here. So so first of all, the sample space is from S, including S, and all the 9999F here. So it's a set with 10,000 terms, but we are unable to write all the possible subset of omega because the power set of omega is 2 to the cardinality of omega, which is like 2 to the 10,000 different subsets. That is impossible to write out. Yeah, that's too many. So it might be, if you write it out, it will occupy more than all of the paper in the world. Yeah, I made another calculation before, like 2 to the like 2552 is equal to 1 library, a common university libraries, all the books. So this is much bigger than that. So since So in this sense, we can use the formula of the Laplace experiment to calculate. So the distribution for S and F, the S is 1 over 10,000 and F is 9999 over 1 over 10,000. This is because there's in the subset of failure, there's 9999 element, and in the subset of success, there's only one element. So this is also not very difficult. So the next example we'll see is like tossing a fair coin twice. Okay, so here we also think about the sample space, which we already see before is a set of 4 elements here. And the probability of tossing head at least once. So first we'll describe the event. The event is HH, HT, TH, which all include at least one H, and here H is gone. So this is the subset representing a tossing head at least once. So here, yeah, obviously A is equal to this set, and A consists of 3 simple events. Omega consists of 4 simple events. So the probability we use the Laplace experiment formula to calculate is at least one head. Probability is 3 over 4. So that is thinking of how to get the result from this probability question. Also, let's see a more advanced example. It's like tossing 5 field goals. Okay, that seems like much more difficult just because the result is unable to write it out all by hand. But once you understand how it works, the logical thinking is the same. So a machine tosses 5 coins at random, and what's the probability of at least 4 heads? So here, first of all, I'll consider what's the possible outcome, the set of omega. So for each coin, it can be either H or T. So it has 2 choice, and if there's like a sequence of 5 H and T, so there will be 2 to the power of 5 by multiplication principle. So there are 32 simple events here. And also, so question asked about the probability of at least 4 heads. We can use another probability as if 2 sets are disjoint, then the union of them is a addition of these 2 sets. So at least 4 heads equal to exactly 4 heads and exactly 5 heads, and these are disjoint events. And exactly 4 heads, there's 5 simple events, which is we can see from the set here. Exactly 4 heads 1, 2, 3, 4, 5, which T can exist in the first, second, third, fourth, and fifth place. So there's 5 simple events, and exactly 5 heads, only 1, because there's only 1 case in which the false sequence is get rid of the T. So there's only 1 simple event, and we use the formula to add them together. So the probability of at least 4 heads is equal to probability of exactly 4 heads plus exactly 5 heads, which is 5 over 32 plus 1 over 32, which is equal to 3 over 16. All right, and there's also another example of like rolling 2 dice. Rolling 2 dice, the cardinality increases with the sample space, which increase from like 32 to 36. But the logic is very similar. So the question asks like, first, how many simple events are there? And also, what's the probability that the sum of the 2 dice is greater than 7? This is relatively interesting. So first of all, how many simple events there? Because the first and second dice are separate, so there's 6 choices for the first dice, 6 choice for the second die, so there's like 6 times 6, which is 36 simple events. And also greater than 7, we can split the event greater than 7 into 5 distinct events, some equal to 8, 9, 10, 11, and 12. And for each of the sum, like sum equal to 12, there's only one possible event, that is 6 plus 6, and 11, 6 plus 5 and 5 plus 6, 10, there's 5 apply, 5 plus 5, 4 plus 6, 6 plus 4, and continue with that logic, you can find 4 simple events for 9 and 5 simple events for 8. And here, obviously we can get sum greater than 7 is equal to like 1 over 32 plus 2 over 32 plus 3 plus divided by 32, 4 divided by 32, and 5 divided by 32. And that is equal to this term. Obviously, so the result is 5 over 12. And that's the result for this question. Also, Laplace experiment is a very simple model, as we already observed here. When you are dealing with Laplace experiment, you only need to know one thing, is like how many simple events are there. But this is not usually able to calculate all of the realistic events. For example, in real world applications, different outcomes are not equally likely. So that will easily break the assumptions for Laplace experiment. Like if you're tossing an unfair coin, a biased coin that lands head 70% of the time, so the tail will only be like 30% probability to toss a tail at the time. So here it doesn't satisfy the assumption for Laplace experiment, so it will not be used. And another example is that it must be finite sample space, but usually, but in some cases, the sample space can be not finite, can be infinitely many, or even uncountably many, which means it is also infinite, but is the infinite can be countable infinite and uncountably infinite. For example, like the countably infinite is the infinity that you can count for, like the integer and the natural number, rational number, they're all countable. But for real number, it's not countable. That is uncountable many outcomes. That is possible. For example, you get the Bitcoin price. It has sample space with uncountably many outcomes, because it can range from like 0 to positive infinity. And here is a set of like of uncountable events. So in this case, we are unable to use Laplace experiment to deal with the Bitcoin price prediction model. All right, so we will now develop a more powerful notion of probability measure. A probability measure is like a formal definition of probability. And of course, we will talk about that in the next week's lecture. And so by this week, if you understand Laplace experiment, and most importantly, the definition of experiment, event, outcome, and also sample space, and that's the most important thing. So next we'll talk about like probability measure, and also some more advanced proving process about that. Okay, so hope you will enjoy this one.